We're ready at this point to talk about non-homogeneous differential equations. So non-homogeneous differential equations are going to be things like, let's say you want to solve y double prime minus 4y prime plus 3y equals e to the 5x. Okay, so let's say that this is what you want to solve. So instead of it being equals 0, you have e to the 5x. That e to the 5x is what makes it non-homogeneous. Okay, so that e to the 5x term is what makes it non-homogeneous. It turns out here's going to be our strategy. One is we're going to solve what I'm going to call the associated homogeneous ODE, ordinary differential equation. So we're going to solve the associated homogeneous ODE, and what I mean by that is pretend that it's homogeneous. Okay, and if you pretend that it's homogeneous, then you can solve it using the methods that we already have talked about. Nothing too much to do there. Call the solution to this associated homogeneous equation. I'm going to call it the complementary solution. So y sub c. So c is for complementary. Okay. So this is I just should write that complementary solution. So that's y sub c. That's the first step. The second step seems a little ridiculous, but it is what it is. Find any, and I mean any, solution to the original ODE. Call it y sub p for the particular solution. And really, any solution will work. If e to the 5x itself works, great. If a constant times e to the 5x works, also great. Really, you can just find any solution at all. There's an art to finding a solution here. Really, it's, I shouldn't call it an art. There's a whole process, a science to finding a solution here that we'll talk about soon. But for now, let's just try and see if we can guess solutions. And then once we have a complementary solution and once we have a particular solution, then the general solution is going to be the sum of these two. So the general solution is going to be y equals y sub c plus y sub p, where this is the complementary solution in the particular solution. So let's see how that shakes out for this example. So we were looking, remember, at the equation y double prime minus 4y prime plus 3y equals e to the 5x. So let's apply this principle. So we have y double prime minus, what did I say? Minus, minus 4y prime plus 3y equals e to the 5x. So first we'll pretend that it's homogeneous and solve it. This is straightforward. Will take us about 20 seconds. This leads us to the equation r squared minus 4r plus 3 is 0, which means that our solutions are going to be r equals 3 and 1, and therefore our complementary solution will be c1 e to the 3x plus c2 e to the 1x, and we're done. I don't know if that was 20 seconds, maybe less. Next, what we're going to do is find a particular solution, y sub p. And what we're going to do is, for now, I'm just going to call it a guess. We're going to guess that we have a particular solution that's some constant times e to the 5x. And remember that our right side was this e to the 5x, so that's why I'm guessing that's what our particular solution is going to be. So we're going to guess that a particular solution is going to be some constant times e to the 5x. We have to figure out what is that constant. So what's the value of a that's going to make this all work? And to do that, well, we're going to take our particular solution and find the first and second derivatives. So notice that the first derivative will be 5a to the 5x, and the second derivative will be 25a to the 5x. And when we do that and plug that back into the original equation, remember that our original ODE was that y double prime minus 4y prime plus 3y equals e to the 5x. That's going to become, well, if we have a particular solution, that means that this is going to satisfy 25a e to the 5x. minus 4 times y prime, which was 5a e to the 5x, plus 3 times a e to the 5x. That's going to be equal to e to the 5x. And of course, we'll have this e to the 5x all the way through. So we can cancel all that. And it turns out what's really going to happen is we're going to look at the coefficients here. We're going to have 25a. So 25a minus 20a plus 3a equals 1, where we canceled the e to the 5x from both sides because e to the 5x is never 0. So we can safely divide both sides by it. And so what's going to happen is we're going to end up with 8a equals 1. And this tells us that a is 1/8. And therefore, our particular solution, y sub p, is going to be 1/8 e to the 5x. That turns out to be a particular solution to this equation. And so once we have this particular solution, that means that our general solution, is going to be our particular solution, which we said was c1 e to the 3x plus c2 e to the x. That's what we did in step 1. Plus the particular solution, which is 1/8 e to the 5x. Okay, and then once we have that, everything is good. We don't really need to do anything else. I think it is worth, just on this first example, checking that this actually is a solution. So let's look at what's y prime. Well, y prime is going to be 3c1 e to the 3x plus c2 e to the x plus, let's see, 5/8 e to the 5x. Y double prime is going to be 9c1 e to the 3x plus c2 e to the x plus 25/8 e to the 5x. And then we want to verify that y double prime minus 4y prime plus 3y equals e to the 5x. Okay, so let's actually just verify what's going to happen here. So this is going to become, let's see, y double prime, this is kind of a mess here, but this is 9c1 e to the 3x plus c2 e to the x plus 25/8 e to the 5x minus 4 times y prime, which was 3c1 e to the 3x plus c2 e to the x plus 5/8 e to the 5x. And we still have to add to it 3 times y, which we said was c1 e to the 3x plus c2 e to the x plus 1/8 e to the 5x. Okay. And from here, what we're going to do is we want to get e to the 5x. Of course, that's what we're looking at. And what we're going to do is we're going to split this up in a few ways. So notice in this splitting up process is actually going to hint to us how this works in general and what a proof would be if we wanted to prove it. But let's look at the e to the 5x terms separately. Okay, so let's factor those out and we'll pull those off to one side and look at those. And then we'll look at everything else also separately. So this is going to be 9c1 e to the 3x plus c2 e to the x minus 12c1 e to the 3x minus 4c2 e to the x plus 3c1 e to the 3x plus 3c2 e to the x. That's all the stuff that's not e to the 5x. And then the e to the 5x terms are going to be plus 25/8 e to the 5x minus 20/8 e to the 5x. There's no point in simplifying. 28 simplifies, but who cares, because we're going to have to unsimplify to add the fraction, so don't do more work than you need to. And then if we distribute the 3, we're going to get plus 3/8 e to the 5x. And now this top part, if you notice, should be 0, because this is exactly what you get when you take the complementary solution and you look at the differential equation, is that you know that this is actually going to solve, where is it? You know that this is actually going to solve this equation, y double prime minus 4y prime plus 3y equals 0. So when you look at that y double prime minus 4y prime plus 3y, what you get and what you should get and what you do get, so these should all add up to 0, because that's how we found that. That's a solution that's going to give us 0. And then likewise, when you look at the particular solution, when you plug it into the differential equation, that's going to give you e to the 5x. And of course it does. We can just verify that this is 25/8 minus 28. That's 5/8 plus 3/8. That's 8/8 or 1 e to the 5x. And so we really do get e to the 5x when we compute y double prime minus 4y prime plus 3y for this particular y. Okay, so not only does that verify that this example actually checks out and that this is a solution, but this gives us an idea of why this works the way it does and how this works in general.